substrate might get inside the enzyme active site. So you can think that the enzyme active site is then operation theater. So it has all the tools necessary for doing the reaction. But only the patient will be changed, right? So the substrate will be changed, so the active site will remain unchanged, so that you can do another surgery on the another patient. So similarly, enzyme active site is the same thing. So what is the interesting part in the enzyme inside the active site? That it brings substrates. So it brings two reactants closer in the active site, because in the active site both reactants are coming together, so they are very close to each other, and also they are close to the enzyme active site. So that is, all the tools are there now to have the reaction, and that effect we call is the proximity effect in the enzyme active site. Then next, another effect that we can see is the orientation effect. What is the orientation effect? Orientation effect, we can see that there are two reactants, so both are at the exact distance in order to have a reaction. And also, like we know that the organic molecule contains a functional group, and only functional group will have the reaction. So those functional groups are very close to each other, so that they can do the reaction. That's what we call is the orientation effect. Then, what are the tools available in the catalytic site or the enzyme active site? The tools are available on the amino acid side chains. Those are mainly the acidic, basic, and other types of groups required for the catalysis. So they play the important role, those acidic, basic side chains of the amino acids. And then at the end, what happens, we know that any catalyst, they cannot speed up the reaction, but what they can do, they cannot change the equilibrium, but they can speed up the reaction by doing what? So if we have this kind of activation energy, which we call the activation energy, that is, if it is very high, because molecule from reactant, it has to climb over this mountain and come to the product. So if this is very high, it will be very slow process. But the catalyst, what it can do, it can provide an alternative, maybe like this, something like that. So it's very easy to climb that mountain now. So that's what they do. They lower the activation energy barrier, and how? By providing some strain on the molecule. Like, for example, let's say we have a carbonyl group, and we want to have a reaction inside the enzyme. So enzyme has the serine, like this type of molecule, right? So that can make a hydrogen bonding, temporary hydrogen bonding. So when it is making the hydrogen bonding, this oxygen is giving some electron to that hydrogen. So now, this oxygen taking all the electrons, so because this oxygen needs more electron, it will pull all this electron here in this side. As a result, this carbon is going to be even more electropositive. Now, another functional group can easily attack that carbon because it is becoming more electropositive. So that type of influence it can do inside the active site by making this type of hydrogen bonding or other interaction. So now we are going to see an example, just for our knowledge, that to know that the enzyme active site not magic bombs. It does chemistry, but you don't need to learn detail about this slide, but you only need to see that how interesting it is, that how the reaction happens inside the enzyme active site. So this pink part, pink part is our enzyme. And we are doing a reaction that is the hydrolysis of a peptide by the chymotrypsin. And we know that the chymotrypsin breaks the peptide bond that has aromatic, like the phenylalanine type. Here is the N-terminal site, and here is so this is the C-terminal site. Here is the another R can be, and here is our C-terminal site. So here, phenylalanine or any other aromatic one, it cuts from the C-terminal site of that amino acid. That is the chymotrypsin job. That's what we learned before. So that's the reaction we are going to see. So now we need to see that what is in the, so this is the enzyme active site, what is available in the enzyme active site. So we can see that at the, what is that number? Is it very great? What is that number? Can you read? It's probably 135. Let's see if I can see from here. 195. So at 195 we have a serine. What does it mean 195? Remember, we start counting amino acid from the N-terminal side. So if you start counting from the N-terminal side, that is the very first amino acid. So if you start counting, so at the 195 fifth position, you are going to get a serine. Similarly, at 57 position, you are going to get a histidine, and at 1 or 2 position, you are going to get an aspartic acid. And they fold in such a way they are very close to each other. Now that play, these three side chains, they play a very important role. And what? So this is our polypeptide chain. And here is, you can see that the phenylalanine side chain, that it has the benzene group. And why this is so specific? Because of this pocket. That pocket is a hydrophobic pocket, and that is very good environment for set up our fit and aromatic ring system. So that's why phenylalanine can get inside that pocket. So now once that is here, now this is the chain, this is our N-terminal site, this is our C-terminal site of the peptide. So this peptide is our reactant, and this is our enzyme. Both are the polypeptide, but one is acting as the enzyme, another one here acting as the substrate. So don't be confused, both are protein here. But this one is the enzyme, and another one is our reactant here. So what is happening now in this group? First, that oxygen wants to make a bond with this carbonyl carbon, but oxygen already having 2 bonds. So what happened? Oxygen transferred that hydrogen as a proton to this nitrogen. And when this nitrogen take that proton, and nitrogen is already having 3 bonds, so what happened? These double bonds shift to make here a double bond, and then this hydrogen shift to that oxygen, because that oxygen is the negative charge, it needs a hydrogen. So eventually this hydrogen moves to that oxygen. So now the oxygen can make a bond with that carbonyl carbon, and this compound is becoming now a tetrahedral geometry, because it was trigonal before, trigonal planar, now it is the tetrahedral geometry. Now what happened next? So now you can see it is making a temporary covalent bond with the enzyme. Then next what happened? That this oxygen reform the carbon-oxygen double bond, and that's the cleavage bond. We know that the peptide bond, that will break down, but when it gets broken, nitrogen needs a proton. And why to get that proton? The nitrogen will take the proton, this proton that was given from the serine, that proton will shift to that nitrogen, and now nitrogen will take back the proton from the oxygen that was given to the aspartic acid before. That will take, and then it will form like this way. And now this is almost, look at that, is the broken part, and this is the C-terminal side. Now it can release from the enzyme. It can release from the enzyme as a broken part. The other part, the C-terminal side, is still attached to the enzyme. So here is the fragmentation part. So now this can get out from the enzyme active site. Now what we haven't used yet, the water molecule, because for hydrolysis we must need the water molecule. Next, the water molecule can get inside the active site, and now the water molecule donate the proton to the nitrogen here temporary and make a bond, that oxygen with the carbonyl carbon, again make a tetrahedral structure. Now this bond gets broken, and oxygen of the serine that is now getting back that proton from this nitrogen, which was taken from the water, eventually now it shifts to the serine molecule, and now this part is also now released from the active site. Now this can get out from the active site. Now enzyme is now the initial structure. So now this enzyme is now again ready to hydrolyze another peptide bond. So it is not a magic box. We can see it's just the organic chemistry is happening here using the different type of side chains. So that's the way an enzyme can catalyze a reaction.